Hi, I'm Jamie Tyler. Thanks for inviting me to give this short seminar. I'd like to thank Brainbox in particular for allowing me to give this short seminar in this workshop at the Brain Stimulation Conference at the Medical University of South Carolina in Charleston, South Carolina. You'll have to forgive me. I'm giving this recording this talk in my truck on a ranch that I just purchased. I'm in the middle of moving, changing career paths and universities. So. Um, I'm going to start off by uh, giving you just my disclosure. I'm a co-founder of IST. We've been commercializing various neuromodulation methods in this space for several years now. I'm an inventor on more than 20 issued patents in the US, another 20 plus patents internationally. Um, I'm also an inventor on methods of and devices for modulating vagus nerve, cranial nerves, and cervical nerves. We have additional IP in the space, and that's my disclosure. Brief background. So most of this group should be familiar with various neuromodulation methods that are used in the field, particularly state-of-art methods, deep brain stimulation, invasive or surgically implanted cervical vagus nerve stimulation devices, optogenetics, and others, including TDCS, TACS, TRNS, and the list goes on. So about 12 years ago, when I started at Arizona State University, I was very interested in the idea of using mechanical energy sources to appeal to the mechanical sensitivity of neurons and neural circuits to determine if we could use those mechanical waves to modulate neural activity. There was some very early evidence from the 50s from the Fry brothers showing that you could, in fact, induce um, activity, or you could reduce activity in cats. Most of this work had been done using high intensity focused ultrasound. And so the real challenge was, could we use low intensity or non-thermal modes of action, pure mechanical waves to modulate brain activity or nervous system activity? Um, the basis of that is that, and this is not really recognized widely across the field of neuroscience, but I think it's becoming more recognized now. The brain is highly mechanically sensitive, right? So it has endogenous mechanosensitivities, many molecular actuators and molecular sensors of mechanical forces, such as actin, which should be familiar to most of you, microtubules, um, adhesion proteins, adhesion molecules, and even ion channels themselves are mechanically sensitive. And so we'll discuss in a little bit that many people have shown now that you can use low intensity ultrasound or pulsed ultrasound and other mechanical low amplitude mechanical forces to modulate the activity of ion channels, including those that are classically recognized as being voltage gated. So our first experiments, I think most of the people in this room may or may not be familiar with this. I think most of you should be. We showed in animal slices and from mice using various optical imaging methods as well as optogenetic methods that we could in fact stimulate brain activity using low intensity pulsed ultrasound. Um, we then went on to show that we could translate those methods, the basic methods, core methods of using pulse profiles that we had developed to modulate the activity of um, certain brain circuits, cortical brain circuits, and deeper brain circuits, including hippocampal brain circuits in rodents and mice. Published that in Neuron in 2010. We also showed a little bit later that in a model of status epilepticus using canic acid, so canic acid induced seizure activity, that we could immediately terminate seizure activity independent of any sensory stimuli. So that was really kind of showing that you could use focused ultrasound in a manner to alter brain activity that was not dissimilar from some of the other methods and achieve similar outcomes. We then spent a number of years through work that was funded by various companies that I've founded over the years. We showed that ultrasonic neuromodulation was safe in large animals. We showed that there was a certain degree of thermal safety, so we weren't heating the brain whenever we're modulating brain activity with low intensity focused ultrasound. And then from a histopathological perspective, we also showed that there was no damage to the cerebrovasculature or the tissue itself. I conducted a series of studies and started to show very first studies showing that we can modulate deep brain activity in larger animals, non-human primates, including baboons and macaques. Some of this work was again funded by one of the companies that I was running at the time. It was conducted in Kenya. Some of the other work was funded by a Ignite award to myself and Dora Sao at Caltech. And here you can see that we were basically started to use electrophysiological methods as well as imaging methods. So that points to one of the nice features of focused ultrasound for modulating brain activity is that it is mostly relatively are readily compatible with standard electrophysiological recording techniques deep in the brain, as well as imaging techniques, including MRI. And this particular one is showing ion contrast imaging. We then, after we validated the safety and that we could modulate larger brain networks using transcranial focused ultrasound, I moved to Virginia Tech and we spent some time characterizing the transcranial focused acoustic fields of these ultrasound waves. And then we targeted primary somatosensory cortex in humans and showed using EEG and other psychophysical methods that we could modulate the activity of very restricted cortical regions using transcranial focused ultrasound in healthy individuals. And again, transcranial focused ultrasound is compatible with EEG, and so I think that makes it opened up a lot of our ability to start to explore how the brain was being altered from an electrophysiological standpoint and how that may correlate with behavior. One of the things that I think is important to point out to the field is, I often have the question is, can you focus ultrasound across the skull? And the answer is yes, you can. And then the second question is, well, what type of spatial resolutions you get? Look, the spatial resolutions of transcranial focused ultrasound for neuromodulation completely shatter those of TDCS or TMS, including any of the kind of more contrived methods such as high definition TDCS or TACS. Here you can see this is from Win Lagone, a former postdoc of mine, showing that they got 0.5 megahertz transcranial focused ultrasound targeted to deep brain regions. And the spatial resolution of the acoustic field, so the spatial distribution of the acoustic field that's being generated by the focused ultrasound, is as small as or on the order of what you can achieve with spinal cord stimulating electrodes or deep brain stimulating electrodes. So if you look down here, you can see this is a standard deep brain Medtronic deep brain stimulating electrode. You can see the spatial extent or the spatial distribution of the electric field that's generated by that electrode. And the spatial scale is the same magnitude as the one that you would have for same resolution that you would have with 0.5 megahertz ultrasound. So it's nice to know that there is a method that can not only reach deep brain regions, but also gives you the spatial precision and resolution that you would have with an inserted or implanted electrode. And that was, I think that's a big deal. That was part of the goal. Since then, supporting evidence has shown from many different studies around the world, Sunshik Yu's lab, Sasha Bystrzycki's lab, Mark George, others have started to get into this field, have shown that you could use transcranial focused ultrasound to modulate primary visual cortex in humans, non-invasive deep brain modulation of the human thalamus by transcranial focused ultrasound from Win Lagone, another paper from Win Lagone showing that they could modulate cortical circuits in a 7T environment. So this is nice, showing that not only is it compatible with, our standard 1.5 or 3T scanner, but it's also with larger magnetic fields or stronger magnetic fields. It's still compatible. So even in the 7T environment, for those of you that have facilities that would provide 7T fMRI. Neuronavigation and TMS, so you can actually combine. There's a lot of work on people combining TMS with focused ultrasound, where they are using the TMS as kind of a search pulse or a test pulse, and the focused ultrasound to modulate brain activity. And so you can see some work here from Win showing this is a focused ultrasound transducer integrated with a standard TMS coil. And then multi-site activation. This is work from Sunshik Yu's lab showing that you could basically use 2 different transducers mounted to these actuators on a helmet and then target different regions simultaneously or interleaved in an interleaved fashion. Work from Leonard Varajan's lab has shown that you can modulate the activity of brain networks in non-human primates in a manner that it causes a persisting change in activity, so a more global or widespread change in activity across networks that last for um, minutes up to hours, depending on the preparation and area that they're looking at. And so you're altering downstream connectivity as well as being able to have a lasting effect. It's not just an acute short-lived effect. Most people are looking at acute short-lived effects just to validate some of the mechanisms of action and the targeting capacity and capabilities. However, it's nice to know that we are also inducing plasticity. So mechanisms of action. Ultrasound has been shown to modulate ion channel currents. We know that ultrasound can modulate the activity of standard voltage gated channels such as NAV 1.5, NAV 1.2, trip channels, TREC channels, and others, right? So we know that TREC channels are polymodal channels that are activated by pH and mechanosensation and others. It's the same thing with trip channels. But these channels have endogenous mechanosensitivities, right? They're essentially springs, protein springs sitting inside of a protein lipid bilayer or spring bilayer, right? And so you have basically actuation of one mechanically sensitive component that's then translated to another. Whether you're acting directly on the membrane or the protein ion channel is not really known now, but people are starting to work on that. Work from Mikhail Shapiro's lab has shown that you can modulate trip channel activity and then cause this amplification through other calcium-induced, calcium release or calcium-induced downstream signaling, calcium-mediated downstream signaling. Work from Lei Sun's lab has shown that you can modulate the activity of the piezo 1 channel. Piezo channel should be on the kind of the everyone's within your recent working memory, I suppose, since it was awarded a Nobel Prize this year for some of the work on the mechanosensitivity of those channels. And so using piezo 1 or trip channels and other channels, one could imagine starting to generate situations where you had something that's very similar to optogenetics, but with mechanically sensitive channels, and I'll talk about it in a minute. Here's other work from Justin Lee's lab, very nice work showing that you could get this plasticity that was mediated by trip A1 channels, so low intensity, low frequency ultrasound activates astrocytic TRP1 channels, and then the synaptic modulation actually occurs via synaptic NMDA receptor activation. Sonogenetics, as I just mentioned, is starting to emerge. This has been led by Shrek Chalasani's lab. He has shown that you could take TRP channels, such as TRP4, and express those channels in neurons that don't natively express the channel, and then start to render control over the channel. They're working very similar to optogenetics, cloning channels from nature. So this is an example of a behavior that's found in a mimosa plant. So a mimosa plant will essentially contract. That's a mechanically sensitive osmotic channel. And here they're activating that channel using pulse ultrasound, 6.9 megahertz pulse ultrasound. So the idea of using purely mechanically sensitive channels from nature and expressing them in systems such as some very similar that we've done with optogenetics, I think is now on the board. So safety, I think this is also something that's relatively it's a major topic, right? And it's present on everyone's mind as you get into these studies. If you're not familiar with ultrasound, it can be dangerous. It does have its caveats. You need to work within certain limits. And so I urge you to use caution, use devices that have been vetted and validated, and make sure you understand what the intensities are, how the intensities are measured, make sure you measure them accurately. You just need to be safe, right? And so with that being said, what we've seen from a couple different reviews and that have collected and looked at really kind of meta-analyses at the literature across several different animal species, we've seen that across ultrasound frequencies, across ultrasound burst durations, different pulse lengths, the different parameters that you start to alter to actuate nervous tissue or modulate nervous tissue with ultrasound. These intensities are safe, right, if they're used properly. And there's a lot that has been written on this. When Lagon has gone in and looked at a series of patients that he conducted, or a series of subjects he conducted over 7 studies, and he looked at the side effects generated by transcranial focused ultrasound, and found that if you look at these, they were really no different than what you would find with TMS or TDCS. Again, I think the potential for danger or damage is probably a little bit higher depending on the tools that you're using. And so, you should be cautious and prudent. Current translational progress, brain and mental health applications, so neuromodulation by focused ultrasound for neurosurgery, neurology, and psychiatry. And SciTech has been working, like they have kind of like one thing that they do, and that's burn brain tissue out. So they have this high intensity focused ultrasound. It's MR guided high intensity focused ultrasound. It's FDA approved to treat essential tremor. I think they've been working on Parkinson's disease, pain, and some other neuropsychiatric conditions such as obsessive compulsive disorder. But this is an irreversible procedure where they use, again, high intensity focused ultrasound. They heat the brain to somewhere above 46 to 48 degrees Celsius for a number, let's say, tens of seconds. And that basically liquefies the brain or causes coagulative necrosis and kills the tissue. So it's no different than an RF ablation, thermal ablation, except that you don't have to insert an electrode or any other type of, if you were doing fiber optics, if you're using fiber optics or a CO2 laser to ablate tissue, you could do it that way with heat. But here you don't have to insert any probes into the brain. It's completely focused through the skull. Jeff Elias has led a lot of the studies to get that work from Inside Tech approved by the FDA. They started working on using low intensity focused ultrasound for brain mapping prior to ablation. So one of the problems when you use MR guided high intensity focused ultrasound to make an ablation is that you cannot identify what brain structure you're in just by MRI. There's no contrast for some of these regions. So you may be very near the sensory thalamus, and the motor thalamus is just adjacent to that. You want to make an ablation in the motor thalamus, but not the VIM and not the VPL of the sensory thalamus. You can't distinguish between those two, so they have to probe. The way that they do this is they transiently heat the brain to subablative levels. It's still heated enough so that they can see the temperature change by MR thermography. Once they verify the beam location, they park the beam and they make the ablation. So the idea from Jeff was to start to use low intensity focused ultrasound for brain mapping prior to the ablation. And in this paper in neurosurgery a few years ago, they did show that they could, in fact, stereotactically map the thalamus. So you can see the VPM, VPL, and different amplitudes and changes of shape in somatosensory evoked potentials. This allowed them to then say, yes, we believe that without heating the brain, using low intensity focused ultrasound, we can start to target where the high intensity focused ultrasound may have an effect using functional outputs. Alzheimer's disease has become a target. There's a couple companies now working on using ultrasound to treat various symptoms of Alzheimer's disease. Some of these include disruption of the blood-brain barrier. There's been some talk about delivering antibodies and other agents, but here we can see that this work in particular has used a shockwave generated ultrasound field, which is a little bit different than what we have done. Some of that has also been language just used to get around some of our early work. But essentially it's a repeated pulses of shock waves that then start to modulate the brain. And this group has shown that they could use this technique to treat some of the memory deficits in patients with Alzheimer's. Neuromodulation for chronic pain has been around for a long time. We've seen transcranial magnetic stimulation. A lot of the weaker methods, such as transcranial direct current stimulation, transcranial alternating current stimulation, and transcranial random noise stimulation, have also been shown to alter pain pathways. I think when we look at some of the more promising technologies, some of the work from Ben He, he's been looking at how he could use EEG combined with focused ultrasound and focused ultrasound alone to control or regulate various perturbed circuits. and pain is one of the big targets. And so they've been working on how they could use transcranial focused ultrasound to treat pain. Mark George's group with Bashar, who is here at the Medical University of South Carolina, has also shown that they could change detection thresholds and pain thresholds by modulating the thalamus in individuals who had pain syndromes or altered pain sensory thresholds. So again, they use low intensity focused ultrasound combined with MRI to do that. And so it's very interesting that pain is going to become a kind of an early target in terms of the physical diseases for treating. We've been working on other kind of like regulation of emotion, regulation of mood, decision making. This is recent work from our colleagues at the University of Arizona. This is a device that we built in a company many years ago. It's actually a focused ultrasound transducer single element that has a convex concave graphite lens and is connected to a power generator touchscreen. This had a full placebo sham mode, but we use this in the study and we're able to show that this device delivering focused ultrasound to the right prefrontal cortex could alter or improve mood and alters functional connectivity in humans. You can see roughly where the brain target was using the focused ultrasound. There's many targets you could go after, right? So if we think about mental health and some of the other like neuropsychiatric diseases that involve like ruminating disorders, or preoccupation, anxiety, depression, PTSD, other stress or disorders, generalized anxiety disorder. There's several different brain targets that you could go after, right? And so there's going to be a fair amount of work that happens over the next year. Should we be targeting the PCC, the MCC, any area of the cingulate cortex? So we should target other nodes within the default mode network circuitry, on and on. But the tools are available now to be able to probe those questions. We had a follow-up study where we looked at the use of transcranial ultrasound in a 5-day intervention and found that in patients that were depressed, we decreased this ruminating behavior or decreased worry. We've done some other work that is in various stages of peer review. We've looked at TFUS for modulation of human response inhibition. This may be a very powerful approach to altering behaviors that we see in substance abuse disorder or certain types of addiction. Modulating emotion and awareness. This is with a 64-channel EEG system from one of my former grad students, Maria Finney. She started to look at what happens when we modulate the dorsal ACC versus the insula, and how does that change emotion and emotional reaction and emotional responsivity to certain negative or neutral stimuli. Again, I think this type of approach is very interesting because you can take this transcranial focused ultrasound and have very precise targeting. We can focus just on certain nodes within the DACC or the default mode network, such as the DAC, and then look at other areas like the insula, and then say like, well, how much of the pars apicularis are we getting? How much of the insula are we getting? And then how does that affect the behavior to be able to identify for target identification, if you will, in terms of treating some of the mental health disorders that are of high interest. Again, it's compatible with EEG. So using focused ultrasound combined with EEG and psychophysical testing, blanker task, other types of emotional tasks, attention tasks, it's very straightforward and very easy, just like you would do with many other types of standard neuromodulation devices in your lab. So current translational progress, I think one area that we forget to talk about a lot of these brain stimulation conferences is the peripheral nervous system and how powerful it is to use the peripheral nervous system to either modulate some disease condition or to modulate a central nervous system condition, right? So we use, for example, peripheral nerve stimulation devices on the head, neck, and face, and those allow us to alter central nervous system activity based on the reticular activating system and neurophysiological arousal. So work from several groups now has shown that you can use focused ultrasound to modulate classic cholinergic anti-inflammatory pathways. If you're familiar with the bioelectronics effort using from Kevin Tracy, he started using vagus nerve stimulation and splanchnic nerve stimulation and stimulation of other subdiaphragmatic branches of the vagus to show that you could decrease cytokine activity. And this has now been replicated, but using focused ultrasound instead of electronics, right? So instead of using electrical stimulation, they're using focused ultrasound, but still targeting the same regions and getting the same types of behavior. In fact, in some cases, it's even better because you don't get some of the cardiac side effects. So GE has done some of this work. Medtronic has done some of the work. The work has been funded by DARPA. They've gone on to show that you could use focused ultrasound and target these different regions, such as nerves that innervate the spleen, to alter these cholinergic pathways that I just mentioned. You could modulate the activity of nerves innervating the liver to alter the glucose metabolism and other types of metabolic activity. Again, non-invasive ultrasound delivered to the spleen for treatment of rheumatoid arthritis. This is work from Hubert Lem's group at the University of Minnesota, showing that they could get a decrease in not only cytokine activity in a model of rheumatoid arthritis, but also in other models of inflammation. Therapeutic ultrasound for reducing the effects of inflammation in disorders such as colitis or other inflammatory bowel syndrome. Again, this is, you could see how you can target the vagus nerve and the splenic nerve, going to different targets, and then for target identification, which one of these is going to give you the best effect or the most desirable effect in terms of the disease you're treating. You can use focused ultrasound for activating the periphery. Neuroimmune interactions for kidney injury. It's another area. Again, like could you use local modulation of these subdiaphragmatic branches of the vagus nerve? Could you modulate it with electrical activity, optogenetic activity, or pulse ultrasound? Now pulse ultrasound is on the field. It's on the table in terms of consideration. I think people are going to continue to look at it in terms of this pathway for reducing inflammation. Peripheral ultrasound is being used for various purposes to replicate sensations. People have used focused ultrasound through the air. So this is called mid-air haptics. You can basically reach out and feel the ultrasound using a phased array. You can focus it, create different objects that people can interact with. You can't see it, but then you can transpose an optical hologram onto an acoustic hologram, an ultrasound hologram, and start to feel and see the sensory stimulus. So summary of the opportunities, we've developed in collaboration with Sonic Concepts and Brainbox, we've developed a turnkey focused ultrasound neuromodulation system. It's very difficult for most academic labs to start to generate this type of technology in-house. You have to build it custom, and so we wanted something that you could just buy off the shelf, start to run it within a few hours, and start to learn the techniques and have the tool that would then allow you to do some of the other science. And so instead of building this from off-the-shelf parts, what we did is we actually went through and protected by our intellectual property, had this collaboration over the past couple of years and launched NeuroFUS, which is a turnkey system, and we're really excited about it. It's sold quite well. Many labs are starting to use it. I think it's the premier system. I'm biased, of course, so take that for what it's worth, but we have cool features built in, such as like you can go search within the software for key papers in the field, and it will automatically populate the waveforms that were used in those papers. So you don't have to go reprogram anything. You can just auto-populate for certain parameters. Future outlooks using broadband phased arrays, flexible phased arrays that are CMUTs or PMUTs, capacitive micromachined ultrasonic transducers or piezo machined ultrasonic transducers that are flexible for wearable devices. That's starting to emerge. We see devices that are made for animals that can ambulate and walk around in cages, very small devices powered by a battery connected to an ASIC and then the ultrasound transducer. Generating holograms, so acoustic holography is very cool. You can start to use certain types of metamaterials to generate holograms, even transcranially. So that's going to allow you to steer the beam to different locations or to generate certain patterns. So future outlooks, and kind of in closing, government, foundation, private industry research for brain and peripheral nervous system applications, the Focused Ultrasound Surgery Foundation at NIH. These are all great places to go to look for funding and partnerships and collaborations. We need to conduct expanded safety studies. We need to enhance visualization and targeting techniques. And I think we're going to hear more about that in a little bit with the K-Plan software, which I think is probably the breakthrough of the past 5 to 7 years in the field for sure. It's going to dramatically change how we start to use focused ultrasound in humans for basic science research as well as translational research. Continued studies on mechanism of action, improved quantitative modeling of mechanisms. So we don't have very good detailed quantitative models of how micromechanical forces are affecting membranes or ion channels, and those things need to continue to be developed. Expanded translational studies and investigations to support clinical applications. Many diseases can be modulated or altered using focused ultrasound, and much work is to be done there. And development and application for high resolution brain machine interfaces. So again, you can use focused ultrasound for neuromodulation and then connect it to closed loop, open loop systems for other types of brain machine interfaces. I'd like to close with this, like science. This is because Mark George, right, who's there at the Medical University of South Carolina. He's become a proponent. When I first started, I had Mark George at a lab at Virginia Tech, and he was such a naysayer, right? He was like, "Oh, you can't focus ultrasound through the skull," and now he's doing the work. So I think it's that's just a testament to where the field has come and where it's going. We now have one of the hallmark leaders in all of neuromodulation, has become a fan and starting to investigate the technology. So with that, I'd like to stop. If there's any questions, hopefully I'm around for the Q&A session and discussion session. And if not, feel free to reach out to me, and I'd be happy to chat with you. Thank you.
Great. Can you hear me okay? Because the audio connection in the other direction is slightly hard. All good? Perfect. So what I want to do, I'll only talk for maybe 10 minutes or so we have a little bit of time for discussion. It's just to kind of pick up on what Jamie was saying about the safety of transcranial ultrasound and where treatment planning sits in that kind of ecosystem of tools and approaches. I'm gonna use K-Plan as a kind of a vehicle to talk about some various things, and I'm going to use the NeuroFUS transducers, but none of what I say is actually specific to that tool or that transducer. I just want to make some general points. So if we have a kind of a focused transducer, so here we have a kind of a focused bowl transducer, this kind of shape. This is one of the NeuroFUS transducers. And we predict what comes out of this transducer. So if we look at the acoustic pressure fields, we get this kind of nice shaped beam. In this case, when we just got an ultrasound field in water, we've actually got really good analytical formula to predict what is the intensity going to be, what is the shape of that beam going to be. So in that case, we're all good. We understand how the ultrasound waves propagate through the medium to give us this kind of beam shape. But of course, what we're doing is we're applying this ultrasound field to somebody's head. So you're probably used to looking at images like these, where you can see lots of kind of structure inside the brain. Actually, to an acoustic wave, none of this structure matters. More or less acoustically, this is all just water, at least in terms of the acoustic parameters. The huge barrier for us is actually the skull. So here I've overlaid a CT image, which shows the bone. And this bone has a really big effect on the acoustic beam. So if I now plot the same transducer, but just moved in the anterior direction a little. So let me just reload the transducer position and overlay the pressure field. You can see it looks quite different, right? So let me put them both on the screen. So here's the free field pressure. And here's now the intracranial pressure after propagating through the skull. And you can see the shape has changed. It's been moved a little bit. It's not as intense. Actually the most intense part is within the skull there. You can see here in this skull layer, that's where the peak pressure is. So understanding how the skull affects that beam is really important for safety, both for mechanical safety, so for making sure you don't do any mechanical damage, but also for thermal safety, so predicting what sort of temperature rise. So the current kind of consensus is that if we stay below a 2-degree temperature rise, then this kind of interventions will be safe. But how do you know if what you're going to apply to the brain is going to stay below 2 degrees? And that's why and where this planning sort of comes into play. So let me switch to a different plan. So let's say you've even got one subject, and you want to know maybe how the skull is going to affect the ultrasound beam. So let me switch views here. If I switch to this view, and we have a look at the pressure. Let me jump to the maximum. So we can predict maybe what the ultrasound field is going to look like inside the brain for one particular position for this particular subject. But if we move the transducer, maybe somewhere laterally, and then we predict the ultrasound field, you can see it looks quite different. Actually, the focus has been shifted upwards. It's in a different place relative to the transducer. So these transducers are in the same plane, and it's been distorted in a different way. So this kind of pre-planning or understanding what the ultrasound field looks like inside the brain is really important, both for safety, but also for targeting efficacy. So if you want to deliver a particular intensity into the brain, then you need to know on an individual basis how much of that energy is lost in the skull. And you can't just produce those numbers from a rule of thumb. Even knowing the skull thickness is not enough. You need to know something about the structure of the skull, which is built up of these cortical and trabecular layers. So you really need to know sort of individual information to kind of help you both locate your focus to the right brain region, but also understand the intensity that you're delivering and the safety profile. If I give you a kind of an extreme example of why that's important. So in this example, I'm going to have the transducer in just one position, but just change the angle, and I'll show you the difference in the acoustic field. That's just loading the images here. So let me change views. I'll change to this view. So if we start off with something that's kind of close to normal incidence, so let me just show you the 3D view here. So the transducer is coming into a relatively flat part of the skull. So everything's kind of lined up. These surfaces are almost sort of coplanar. And then we look at the acoustic field that we produce. It looks kind of nice. It looks kind of like, you know, sort of similar to the beam that I showed you in water. But if we start to tip the transducer slightly, let's say we sort of move it by 20 degrees, and then have a look at the pressure field, you can see it's starting to become quite distorted. And then if we go to the extreme of tipping it, you know, by 40 degrees, because of the acoustics, the beam is completely different, right? So there's almost no focus inside the head. So understanding this before you go putting a transducer on somebody's head is really important, and that's, you know, what these kind of tools are designed to help you with. So that's kind of the acoustic part of it, and of course from these types of simulations you can extract things like the intensity in the brain, the mechanical index, and other safety profiles. The other side of the same coin, of course, is the temperature. So let me show you another example. In this example, we've just got a fixed transducer at a fixed position, and what I'm changing is the focal length, but I want to show you the difference in the temperature profile this time. So let's just load this one. I'm going to switch to this view. So here, let me jump to the maximum. This is an annular array transducer, so you're able to move the focal distance electronically. And you can see I've run various simulations with different focal lengths. So if we look at the pressure fields, you know, as I change the focal length, understandably it gets sort of further away. That's fine. That's what we kind of expect. But maybe what you wouldn't expect is that the temperature profiles, so same transducer position, same skull, also change. So let me turn off the pressure field and now look at the temperature. Turn off the skull. So as we increase the focal length here, the temperature increase, sorry, that's the pressure. The temperature increase kind of spreads out over the skull area. So like the temperature is spread out, and that kind of makes sense if you think as you focus further away, your focusing triangle is getting bigger, so you're like spreading the energy out. And the last thing I want to say is just about the pulsing parameters that you choose. So Jamie pointed out nicely that there's a nice range of these different pulsing parameters that have been shown to upregulate and downregulate different types of neurons. So you might be changing the types of stimulus that you use in the brain, but of course they also have an effect on the safety profile. So I'm going to show you this view. So let me load transducer. So let's just look at the pressure first. So this is the acoustic field. It's focused here just on the other side of the skull. And for all of these I'm about to show you, it's the same acoustic field, but I'm just changing the stimulus parameters, like how long I leave the acoustic field on for, the duty cycle, and so on. So let's look at the reference. Turn off the CT. So this is the heating inside the skull bone. The reason you get more heating in the skull, I should say, is because you have more acoustic absorption. So more of your mechanical energy gets turned into heat here. So this is for a 300 millisecond stimulus every 3 seconds for 15 repeats. So that's our baseline here. And we get a temperature rise of 0.9 degrees. So that's within our 2-degree limit. If we have a shorter interstimulus interval, maybe that's something you want to try. So instead of stimulus every 3 seconds, you do the same stimulus but every 1 second. You get a sort of a more focused heating profile, and now you're heating by 1.3 degrees, right? So it really matters, those parameters. If you change the duty cycle, so you're doing 300 millisecond pulses, but you have a duty cycle of 50%, then you lower the temperature increase. So in this case, it's a 0.4 degree temperature rise. Or if you keep the same stimulus and you just do twice as many of them, so 300 millisecond stimulus once every 3 seconds, but you do 30 of them, then again you get a bigger accumulation of heat in the skull. So in this case, we have a 1.1 degree temperature rise in the skull here. So understanding all of that in terms of if you're designing a stimulation protocol, understanding both, those parameters that you choose are going to be affected by the skull, and then thinking about the safety profile of what you're doing in terms of skull heating and mechanical and thermal indices, I think is quite important. I'm going to stop there because I think we're almost out of time. Maybe there'll be time for 1 or 2 questions. I'll hand back to you on the floor, Mark.
Can you skip JVC with us, or just you? Any questions? So does this does K-Plane have the capability to simulate CMUT transducers?
I'm really sorry. Can someone relay that to me? The audio connection is super sketchy. I'm really sorry.
It might just be my mask too. Does the K-Plane system have the ability to simulate CMUT, EMUT transducers?
Yeah, so the acoustic field is not so much dominated by the technology you use to generate the wave, but more to do with the shape of the transducer that you use and the acoustic output from it. So in short, yes, you can. As long as you know something about it, like the shape of it, like say the bandwidth, the frequency response, then you can model it, yes.
So we don't need to do a full characterization of the transducer to use this system. We just need to have the output and the shape of the transducer.
So the bare minimum is just knowing something about the geometric properties of the transducer. That will get you some way. If you have some calibration information, your model will be infinitely improved. Well, not infinitely, it will be improved somewhat. So if you have some line scans, you know something about the focal intensity, the focal size, then you can use that to tune the models quite a lot. So you get a better map with what you would measure in a water tank. So yeah, you can start with book values. That gets you some way, like, just off the shelf, how big is it, what shape is it? But if you have some calibration information, which for the NeuroFUS, and I assume it's similar for others, is already measured by the manufacturer, then that allows you to kind of tune your model to your kind of individual device.
Thank you. I have a question about the ultrasound effect on the human. Not many people have that experience to feel the ultrasound of their daily life. So what the genetic evolution advantage for the human to develop the mechanical receptor or ultrasound receptor to sense the signal of the ultrasound?
Is that a question for me? I'm sorry, I'm really sorry. It's very hard to hear.
He's asking about evolution in ultrasound and why we would have a receptor that would be mechanoreceptive, especially in our system, considering what evolutionary advantage do you think that would have?
In terms of mechanoreceptors, in terms of the on the neurons, you mean?
Yes.
That's not a question I can answer. I'm afraid I'm an engineer, not a neuroscientist. That sounds like it's a question for Jamie. I'm very sorry, I don't know the answer.
To be the first speaker.
Yeah, Jamie's not able to join us. If he was,
And Brad, what do you do if you don't have a CT scan?
Very good question. These days you can get really good simulations as long as you can take some kind of structural skull image. So ZTE is my favorite. So I think you can do that on GE and Siemens scanners now. So as long as you can take some kind of skull image, then you can get a pretty good simulation. If you literally have nothing, then you could do a segmentation of a T1 weighted MR or something. That would get you some way, but it's not going to be as good as having an actual image of the skull. But you do pretty good with ZTE if that's like that zero echo time imaging on an MR.
Do you have an indication of the error rate for MR versus CT?
Could someone just relay that back to me? Sorry, I'm really sorry.
Is there any indication of the error between these MR models versus the CT?
If you have a ZTE, the errors can be really small, especially if you can map to the acoustic properties in a smart way. So we actually use a learned model to help us bootstrap a ZTE into acoustic properties. And in that case, our acoustic simulations show maybe 1 or 2% difference, so almost nothing. So yes, if you do it in a clever way, then the differences can be very small. If you've ever looked at a ZTE image, they almost look like a CT, so it's not surprising that you do really well. You see really good structural contrast. If you're using a brain segmentation, the errors can be much bigger because basically you're skipping the internal structure of the skull. Like if you just got a T1 weighted image and put it into the FSL toolbox and did, a single layer skull, I mean, you get the basic morphology, so you'll get the basic refraction, but you're missing all the internal structure. So in those cases, the errors can be much, much bigger if you don't know anything about the skull structure. Pretty good if you're going through like the temporal bone where there's not much structure anyway, but not so good if you're going through a bit of the skull where the inside is quite wacky, or you have lots of trabecular bone, for example.
We've got a couple of examples as well. So if you want to come by the booth, we've got like the paper that Brad's described now, basically. There goes one more.
Yeah, we just kind of wanted to follow up on that. Essentially, you're just assigning a density map. Are you just taking value from literature and assigning it to bone, assigning it that density to bone and scaling it up and down with the image density, or if there's any pathology like some sort of density bone density problem, is that something that's going to change the measurement dramatically, as you know?
Yeah, so what we do, let's say you have a CT scan, so I think that's what the question was. You can map from the Hounsfield units to the mass density quantitatively. So you have a very accurate map of the density, the mass density of the bone. And then there's a really good correlation between the mass density and the sound speed locally. So you have a heterogeneous map. So actually your map of the sound speed and density looks pretty much like these skull maps. If I was to plot the sound speed, it would look like this. It would have this kind of, oh, you can't see my screen anymore. So I'm pointing at my screen. It would have this kind of structure. So we directly map from the CT Hounsfield units. For the attenuation, we use experimentally derived values. So us and quite a few other groups have spent quite a lot of time in the lab with ex vivo skulls trying to characterize the gross attenuation for these types of samples. So that's where we get them.
Yeah, is there sorry to harp on this. Is there a lot? I'm an MR person, and I'm curious about trying to use MRs instead of CTs on this. And is there a big correlation between the Hounsfield units? Those go with density pretty straightforward, but zero echo time and ultra short echo times I don't know. Does it correlate very well with density, or are you going to get the same result? Just
Yeah.
concerned that there's other factors in there that are going to screw up the measurement.
Yeah, it's a good question. So there's two different ways to do it. One way, the way you do it is to use a deep learning model to map from a ZTE to a CT with the correct transferred units. So that's one way. The other way to do it is just to basically rescale your ZTE or your UTE based skull, let's say between 0 and 1, where 0 is like the most porous, it's like water, and 1 is like the most bone. And then you would just use book values for cortical bone, like the thickest part of the bone, and for brain. And then you basically use your ZTE as like to interpolate between, you know, no bone and all bone. So in every voxel, you know, this voxel has a value of 0.7, so therefore I'm going to use 0.7, the value of the maximum sound speed and density that I could get in the skull, that kind of thing. This idea of you're basically measuring bone porosity in a sense, and then you're mapping from porosity using a mixture model to sound speed and density.
Thanks. Last question, I promise. And does K-Plan do this? Does K-Plan do this? Is K-Plan aware that you're giving it an MR, or is it agnostic to what density map you're giving it?
Yeah, K-Plan can map from all different types of medical images. The deep learning part is not in there yet. That's still under development, but you can give it any type of skull mask, yes.
And it will treat it differently if it's an MR versus if it's CT?
So if it's just a T1 weighted MR, it will fail. You need to do some work first. So you need to segment the skull out or something. But if it's a structural image, like a ZTE, then it can handle that, yes. Yeah. So it doesn't do the segmentation automatically. So if you literally have a T1 weighted MR, you would need to run it through FSL or FreeSurf or something and get a skull mask first, and then put the skull mask into K-Plan. So it's not a segmentation. K-Plan isn't a segmentation tool, but if you have something that's structural like a ZTE, then it will take care of that, you know, the porosity mapping bit I just described.